Okay. So we're recording. We're recording. Great. All right. Does everyone have the packet? The key? The packet, the key. I'm recording now, so it'll post on that page later for you to refer to the rest of the week. All right. So remember that this is our last midterm exam. It's one of the easier ones. And it covers all of chapter 19 and then up until what we covered today in chapter 20. So just up until the Nernst equation, delta G, E, K, all of that. So you'll see at the bottom of this page is the copy of the supplemental information that you'll get. So you'll get the typical stuff you get, temperature conversion. I don't think you'll need pressures, but they're here. KW, I don't think you'll need it, but it's here. But most importantly, Faraday's constant, and there you see the joule conversion. 1 coulomb volt is equal to a joule. So that's really important for one of these equations, this one right here, that the delta G equation, in order for us to, we understand the signs that a positive cell potential means a spontaneous reaction. So delta G has to be negative. But we see here is that, cell potentials in volts, Faraday's constant is like something weird, but just have blind faith when you plug all of these numbers in, you get a joule come out. But oftentimes you have to convert that to kilojoules, all right? I don't know why this equation's here. You don't need it. But it's there. I think it's an artifact from a previous instructor, but what you see here is we went over these 2 equations today relating E to delta G. Therefore, E is also related to K. Since these 2 delta G equations are related, E is related to K as well. And then finally, the Nernst equation for non-standard conditions. I like to think these 2 equations, our Nernst equation and our delta G without the not equation, they are the same equation. You squint your eyes, they're actually the same equation. You start with, the value, the thermodynamic value at standard conditions, and then you just use Q to adjust for, oh, these are the actual concentrations you're at. All right, so let's go through it. Let's do chapter 19. I think it was the somewhat of a longer chapter. There's more concepts there in chapter 19, entropy and Gibbs free energy. So let's work on. Let's do this. Everything. Yeah. Okay. All right. So So we talked about chemical thermodynamics. This chapter had 2 different sections: entropy and Gibbs free energy. So the first part of the chapter, we looked at spontaneous reactions in relation to entropy, because what we know is as entropy of the universe increases, those are our spontaneous reactions. So we were always looking for positive entropy changes of the universe, right? While Gibbs free energy of a reaction, so simple reactions, we were looking for negative values, right? And then in chapter 20, we saw, spontaneous electrochemical cells, they had positive cell potentials. All of these are related. All of these describe spontaneous forward reactions, all right? Okay, so yeah, for any spontaneous reaction, entropy change of the universe is positive. So we looked at conceptually what entropy is. There's a couple factors. So this is a common exam question to order these different substances in increasing entropy. So we're assuming that we have the same amount of each of these substances. So we're looking at different factors. But if we wanted to list all of the different factors that increase entropy or increase microstates, temperature is one of them. So temperature, number of particles is another one. So if we had 1 mole versus 2 moles versus 5 moles of substances, 5 moles would have the most entropy, while 1 mole would have the least. So in these examples, we're assuming temperature and number of particles are consistent. So what we're actually looking at are the other factors. So I think some of the other factors, the most common one is phase. What else is there? Complexity. Molar mass. Is there another one? Oh, volume. That's the weird one. So I should actually, that one should be up here. I'll change these numbers. Okay. Volume. Yeah, that's the weird one. 4, 5, 6. There we go. So basically for these three, these examples, we're assuming temperature, number of particles, and volume are the same for them. All right. Because I'm just telling you like substances. I'm just saying like helium gas or hydrogen gas. We're assuming all of those factors are constant. So really what we're looking at are these, the last three factors. How are the phases different? How are the complexities different? How are the molar masses different? So if we look here in terms of complexity and molar mass, I would say that hydrogen has the least amount of entropy because it's the lightest, smallest little particle. So hydrogen's going to be last. So then our other factors or other compounds all have like hydrogens, chlorines, and oxygens attached to them. So at this point, I would probably say, oh, molar mass is probably going to affect us the most. But actually, it's molar mass and probably complexity also. Because if you notice here, HCl is just a molecule, so it's just kind of like bouncing like a spring. But HClO actually has 2 bonds, so it's going like this. And then HClO4 has like a bunch of bonds on it. So that's definitely vibrating the most. So I believe the ordering should be H2, HCl, HClO, and then HClO4, right? So here we're just looking at, and because all of them are in the same phase, they're all gases, that's why I was looking at molar mass and complexity. Versus the next one, it's the same substance, but notice the only difference are the phases, all right? So in this case, phases will probably be the factor here. It's going to be solid, liquid, then gas, because each of those compounds on their own have the same molar mass, have the same complexity. All right, so that's a common exam question, ordering them. So again, notice that you're going to assume temperature, number of particles, and volume stays the same for all of those. Same thing for this next one. Here, I'm assessing the same thing, but in the context of a chemical reaction. Here, I'm asking you, how is entropy changing from reactants to products? So if we look at this, we're going from things that are aqueous, dissolved. So in your mind, think about what that looks like. You have a solution, those ions are freely moving through it, versus on the product side, we have a solid. So what do you think, and how's entropy changing there? It's going down, yes, because we're going from free things to not free things that are all stuck at the bottom. So that means the change of entropy of this reaction is going to be negative. We could take the table values, do products minus reactants, and we'd probably get a negative entropy value. All right, the next one, B. Sometimes just looking at particles, particularly looking at gas particles, is going to help you the most, because I see, oh, there's solids on both sides, but the product side also has a crazy gas on the product side as well. So I would deduce that entropy is increasing, that it's positive because that gas is being formed. Right? And then this last one, what do we think the sign of entropy change here is in this reaction? Probably gonna be negative, yes, because we're going from 3 gases to 1 gas. Or sorry, no, 2 gases. That's probably gonna be the determining factor there. All right, perfect. Okay, good, you'll knock that one out real quick. All right, so here's some other conceptual things. All right, a combustion reaction is always exothermic and always has a positive delta H of reaction, enthalpy of reaction. Yeah, no, boo. Yeah, what's wrong with that statement? It's negative. Yeah, this is a negative delta H of reaction, yes. Heat is released. It's released. The reaction loses heat and we gain it. Yes, okay. A decomposition reaction always has a positive entropy change. If you don't know, just write one. Write a decomposition reaction. When something decomposes, you have one thing and it becomes 2 things. I don't know, that. So what do you think? How does entropy change in that? Yeah, so since you're going from one thing to multiple things, yes, this is true. So this first one was false, this one's true. Decomposition reaction always has a positive sign of entropy. What about a combination reaction? What do you think? Negative, yeah, because you're going from lots of stuff to only like one thing. Okay. The second law of thermodynamics says if delta S of my reaction is positive, the reaction is spontaneous. No, but I thought we were always looking for positive entropies. It's the universe. Yeah, so this is incorrect. This is incorrect because it should say delta S of the universe. There's a difference. There's a difference. Because when you did the salt lab, or like you did the calorimetry lab or something, there's some salts that spontaneously mix and are exothermic. There are some salts, you dissolve them and they spontaneously are endothermic. They happen because of entropy, where delta S of the universe, we want that to be positive, but that is equal to the sum of the reaction and the surroundings. So your reaction can be endothermic, or delta S of your reaction can be negative. It can be negative, but as long as the surroundings is big and positive, then overall the universe change is still positive, and this is a spontaneous reaction. If you had a reaction where delta S of the reaction was positive, but the surroundings got really, really, really cold, this would be not spontaneous, all right? So don't just think, oh, entropy change needs to be negative or positive. It has to be entropy change of the universe, which is the sum of the reaction and the surroundings, all right? Okay, so yeah, this one is false. You're looking for positive universes. Okay, if delta S of the reaction is negative, the reaction can still be spontaneous if delta S of the surroundings is very positive. So I think this is just what I just said. The second law says, okay, delta S of the universe must be positive, and that is equal to the reaction plus the surroundings. So this question is saying, okay, delta S of the reaction can be negative if the surroundings is very positive. So is D true or false? It is true, because a little negative number plus a big positive number will still get us a positive number to be spontaneous. This one is true, right? This is actually an example of the hydrogen balloon demo. Let's look at that. So this is basically the hydrogen balloon demo. Every time I do this demo, the reaction actually loses entropy. The reaction loses entropy. But it's a spontaneous reaction. Once I light it, boom, it goes on its own. And it happens because it is so highly exothermic that the delta S of the surroundings is so positive that the overall universe change is still positive, even though the reaction is actually losing entropy. Right, so that's an example. All right, so let's see the next one. If surroundings is very positive, the reaction is very exothermic. That is true. And the equation that helps us determine that is the delta S of the surroundings is equal to negative delta H of your reaction over the temperature in which it occurs. I like to think of it this way. An exothermic reaction releases heat into the surrounding. It heats up the surroundings, so the surroundings increase entropy. Or an endothermic reaction has a positive sign of delta H reaction. It steals heat from the surroundings. So the surroundings lowers or decreases its entropy. So you see how it's the opposite sign of whatever the reaction is. So this one is true, because exothermic means negative delta H reaction. So surroundings would be positive though. All right. Okay, and then the last one, when they forward and reverse reactions are both spontaneous, the system is at equilibrium. This is also true. That is true. Okay, perfect. Okay, so how else can we think about free energy and this chapter? So other things I can ask you is, okay, I can give you information about the enthalpy of a reaction and the entropy of a reaction, and you can tell me some stuff about when is this reaction spontaneous or not. So in this example, I give you the enthalpy of vaporization for a reaction and the entropy of vaporization of a reaction. Calculate the boiling point temperature of this substance in Celsius. So the idea here is we're going to use the equation of Gibbs free energy, delta G equals delta H minus T delta S. This equation is a lot more useful to us because now everything is referenced to the reaction. I don't have to think about the reaction and the surroundings at the same time. Everything is in terms of the reaction. And I'm asking you calculate the boiling point temperature of this thing. So I'm taking a liquid and turning it into a gas. So at the boiling point temperature, liquid and gas exist at the same time. Think about when water boils on your stove. It doesn't all instantly become a gas at the same time. It stays at 100 degrees Celsius while you still have all that gas and a ton of liquid still in your pot at the same time. So we are at our boiling point temperature when both of these exist at the same time. So we're at actually equilibrium at that temperature. So just like in that previous question, we say a system at equilibrium has a delta G of 0. Delta G changes a lot drastically. Delta H and delta S don't change as much drastically at different temperatures. So what we're going to do is just set that equal to 0. And I give you these the values of delta H, delta S. So we're going to just calculate what is the temperature required to force delta G to be 0. That is the equilibrium, the temperature at which equilibrium is achieved for this system. So just make sure that these units match. That's probably the biggest thing. All right. So delta H of vaporization is 59.11 kilojoule per mole minus temperature. That's what we're solving for. And then entropy, this is in joules. So we need to make sure that that is in kilojoules. So 0.0929 kilojoule per mole Kelvin equals 0. So I think what we get is temperature. If you move stuff around, I think it's temperature equals delta H over delta S. Just make sure that those units match. And so in this case, that answer is, what did I say? 636.3 Kelvin. Okay. But Kelvin is not a temperature on my thermometer. So I want to convert that into Celsius. So subtract 273 to get that in Celsius. So this is 363.1 degrees Celsius is when mercury will boil. Cool. All right. Yeah, so predicting boiling point temperatures, freezing point temperatures, you set delta G equal to 0 and use those thermodynamic quantities. All right. Okay. Without doing any calculations or looking up anything, predict the spontaneity of this reaction. Oh, do you want to get your stuff? You can come, it's fine. You can get your stuff. No? All right. So this reaction is never spontaneous or spontaneous at high temperatures, low temperatures, or whatever. So in this question, we are deducing this same delta G reaction. We're using delta G equals delta H minus T delta S, all right? And so remember with delta G and spontaneity, we were always looking for positive universe entropy changes for spontaneous reactions, but we here are looking for negative delta G of reactions to predict spontaneity. So we're asking which temperature range gives us a negative Gibbs free energy change. But I have a problem. What the heck is delta H and what the heck is delta S? I didn't give it to you, but I gave you hints at it. Yeah. So what did I say about this reaction? I say it's what kind of reaction? Combustion. It's burning. It's burning. So what is the sign of delta H? Negative. Yeah, exothermic. So that's the hint. That's the hint. Right? So there, that's the sign of delta H. It's negative. But what about entropy? Well, we can look at the reaction itself and predict what is the sign of entropy. We are going from what? 6 things to what? 7 things. So what do we think? Yeah, entropy is going up. So delta S of this reaction should be positive. Delta S is positive. So, sorry, positive. There we go. So now we ask ourselves, we want a negative value of delta G. What kind of temperature will make that happen? What happens when temperature is really small? What's the sign of delta G? So a negative number minus a positive number is still negative. But what if temperature is really big? A negative number minus a big positive number is still negative. Yes, so the answer will be this reaction is always spontaneous. It is always spontaneous. All right, because of the sign of entropy. If entropy was negative, we like did this and saw it was negative, it would be a little bit different, right? Because we see any temperature from 1 Kelvin to 1 billion Kelvin, delta G will always be negative. And it's all about inspecting the signs here. Okay. All right. Is that what the answer said? Yes. Cool. All right, let's keep going. All right, let's look at this reaction. Let's calculate delta G, delta H, delta S for this reaction at 298 for this reaction. So notice that it's 298. This is standard conditions. We are allowed to use table values, okay? So finally, you guys can use the entire table. So how do we calculate the delta G, all of these for the reaction? What are we doing? What are we doing? Products minus reactants, yeah. Table values, we're gonna just simply do products minus reactants. So I'll just do one of them. So just remember that we have, these are our thermodynamic quantities. We need to make sure we use the appropriate, stoichiometry here. We're just gonna do products minus reactants. I like to highlight it. So here are my yellow ones are my 2 products, and then my reactant is this pink one. So I just need to make sure I do 2 times hydrogen for all of these and 3 times my methane. So let's do the first one. Gibbs free energy for this reaction is equal to the C3H8. So I think that's propane. So negative 23.47 plus 2 times those hydrogens. So 0, perfect. Minus all of the reactants. So here are the reactants, negative 50, but 3 of them. 3 times negative 50.8. And so we get that this value is positive 128.93 kilojoules for that reaction. All right, and then we do the same thing for delta H and delta S, where it's this yellow one times plus 3 of these yellow ones minus, times 2. 2 of those. Times 2 of those hydrogens minus 3 of those methanes will give us the overall for that reaction. So I'm not going to do it all 3 times. It's just going to be the 2 yellows minus the pink for all of these, but I'll write those answers. So when we do products minus reactants for delta H of the reaction, what unit comes out? Look at the table, kilojoules. It's going to be kilojoules. But then when we calculate delta S of this reaction, what unit comes out? Joules per Kelvin, joule Kelvin, right? Okay. So yeah, products minus reactants for all of those, make sure you use those stoichiometry. Do I need to do them? Do I need to do products minus reactants? No. No? No. Okay. No, so let's use them, all right? Let's calculate K for this reaction at 298 Kelvin. So what equation do you think is going to help us? Let's just go down to the supplemental information real quick. Which equation is going to help us? The second one, right? The second one relates Gibbs free energy for a reaction to K of that reaction. If we start this reaction at standard conditions, the value of like whether delta G is really positive or really negative tells us which direction that reaction has to go to achieve equilibrium. So we have delta G, R is a constant. We know the temperature. We're just going to solve for K. So simply, we are going to use delta G naught equals negative RT ln K. We're going to plug in that delta G we just got. So positive 128.93, but this needs to be in joules. So 10 to the 3 joules equals negative 8.314, temperature 298, ln of K. So solve for K. Solve for K. And I think if you solve for that, you get K is equal to 2.51 times 10 to the negative 23. So at equilibrium, reactants are most present. If you look at the sign of delta G that we solved for earlier, it's a very positive number. So is this reaction really spontaneous? It is not. So a very small value of K makes a lot of sense. This reaction Doesn't need to move in the forward direction at all to achieve equilibrium. It actually has to move backwards. It has to produce more reactants in order to get that small value of K. All right. Let's calculate delta G for this reaction that occurs on the surface of Venus. So notice the temperature of the surface of Venus is 748 Kelvin. Is this at standard conditions? It is not. All right, so that means we can't use, it's not, so the Gibbs free energy for this reaction on Venus is not the same as delta G naught. This is delta G on Earth at standard conditions. But on Venus, it's going to be different. So here we have a different temperature. We're going to assume that delta H and delta S are constant. So we can use the equation delta G equals delta H minus T delta S, and we're just going to shove that value, that different temperature in this delta G equation. I didn't actually write the answers to these. What were the answers? This is the enthalpy of this reaction is positive 120.55. And entropy is negative 27.84. That's what my key says. Hopefully the key is right. All right. So that's my entropy. There is my enthalpy. I'm going to plug those numbers in with this new temperature. So again, make sure your units match. I'm going to put everything in joules. So delta G equals the enthalpy. So 120.55 times 10 to the 3 joules minus the temperature. So 748 Kelvin times the entropy. I didn't give myself enough room. Times the entropy, negative 27.84 joule Kelvin. So what you see is that those Kelvin values, they cancel. So it's a joule minus a joule. Great. So we see that delta G at this new elevated temperature is 1.41 times 10 to the 5 joules. So we see it's much different than at standard conditions when we're at this different temperature. So we'll just use the delta G equals delta H minus T delta S equation for this different temperature. We can do that because delta H and delta S usually remain somewhat constant at different temperatures, but delta G changes drastically at different temperatures. Okay, so let's calculate what are we calculating? K for this reaction on Venus. So we did this earlier. Oops, sorry. We did this earlier, but for the reaction at 298, this was at standard conditions. This was, B was at standard conditions. So we were allowed to use delta G naught that we calculated before because it was at 298 Kelvin. But on Venus, this is non-standard conditions, all right? Non-standard. So we have to calculate a new value of delta G at this new temperature at 748 Kelvin. But thankfully, we already have that number. We're actually going to do the same thing we did in B, but we're going to use this new delta G value we got that was measured at 748 Kelvin. So we're still going to do delta G equals negative RT ln K, but we're going to use the delta G from part C, and then we'll stick in that temperature again right here. So what we get is what? So 1.41 times 10 to the 5 equals negative R 8.314. The new temperature, 748 Kelvin ln K. So you solve for that K, and I think you get K is 1.34 times 10 to the negative 10. So this reaction's still not very spontaneous, but it's actually more spontaneous on Venus than it is on Earth, probably because of that elevated temperature. All right. Okay. Cool. Let me think about this. Yeah, okay. So yeah, this example, this question had you calculate delta G and K at one standard condition. So that means you can just go ahead and use table values, delta G naught, but it also had you do it at a non-standard temperature. And so that's where we use this equation, delta G equals delta H minus T delta S at a non-standard temperature, and then relate that to negative RT ln K. All right, with that new elevated temperature. Okay. All right, keep going. Oh, wow, just one more question. Okay. So let's look at this example. So remember, entropy, Gibbs free energy, K, they're all related by those different equations. So let's write the KSP expression for this reaction. So I give you that the KSP for this salt, chromium hydroxide, is this value. So let's write that KSP equation. So remember, KSP, SP stands for solubility product. So what we want to do is throw this thing in water. It's a solid, throw it in water. Think about what ions do you get? You get a chromium 3+, and you get 3 hydroxides. All of those are aqueous. So that means the KSP expression, KSP equals the maximum amount of chromium 3+ you can get times the hydroxide concentration, but it is cubed, right? And I already tell you that this value, KSP, is equal to 6.3 times 10 to the negative 31. So this thing is not very soluble at all. It's not very soluble at all. So that means this reaction, does it go in the forward direction that much? No, it doesn't go in the forward direction that much. So what we should anticipate is that Gibbs free energy is going to be a very positive number. That, only reactions that are spontaneous in the forward direction typically have negative values of delta G, but this value has a very small value of KSP of K. The reaction remains on the reactant side. So this is going to have a very positive value of delta G. But let's prove it. We are calculating delta G naught. So this is at 298 Kelvin. So we're simply going to use the delta G equals negative RT ln K. I gave you K. We know temperature is 298. R is a constant. So we just plug in all those things. So negative 8.314, temperature 298, ln K is natural log of that little number, 6.3 times 10 to the negative 31. And so I think if you solve for that, you do get, in fact, a very positive number of Gibbs free energy. You get delta G equals 1.7 times 10 to the 5 joules, or 170, kilojoules for this reaction. Very positive, because the forward direction is not very spontaneous. K is very small. Okay, so what is the value of delta G of a saturated solution of chromium hydroxide at equilibrium? So this is kind of a trick question. Trick is I say at equilibrium, so delta, and note it's delta G without the naught. Okay, so if we're at equilibrium, is the reaction going to shift to the left or the right at all? Nope, it's going to just stay there. So delta G is actually 0. It's happy there. It's going to stay there, right? But for a saturated solution, delta G naught is still the same number. It's a constant. It's a value at standard conditions. But if we're at equilibrium, we're not at standard conditions. So delta G naught never changes, all right? But delta G, the push for this reaction to move left or right at these conditions will be 0 because we're already at equilibrium. All right, finally, will a solution that is made to be this concentration of chromium with this pH produces precipitate? So let's figure it out. So remember, KSP equals chromium concentration times hydroxide concentration cubed. I'm telling you how much of each thing you have right now. So I'm setting up Q conditions. And we're going to do the, compare Q to K, see which way the reaction has to shift. So let's try it. We have the chromium concentration just given, but the pH tells us what the hydroxide concentration is, right? So if pH is 7, that means POH is 7. So that means that the hydroxide concentration is 1 times 10 to the negative 7. Agreed? Agreed. Okay. So chromium 3 plus, so let's plug in these numbers. So chromium 3 plus is 0.1. Hydroxide is 1 times 10 to the negative 7, but this thing is cubed. And so if you calculate this, I think you get that Q. So we're calculating QSP. These are the actual concentrations that are given. Q is equal to 1 times 10 to the negative 22. All right. While K is times 10 to the negative 31. So compare these two numbers. All right. Compare those two numbers and then think about it in the context of this chemical reaction. Q is what? Bigger or smaller than K right now? It is I know they're small numbers. They're both small numbers, but which one is less small? Q. Yeah, Q is bigger than K. So what does that mean? Go back to your chapter 15. If Q is bigger than K, you have too much products. Yes, so Q or K is always products over reactants. So if Q or K is a big number, you have a lot of products. So if Q is bigger than K, you have too much products right now. So which way will your reaction shift? Backwards. What should your eyeball see? Solid form. Solid should be formed. So let's think about it this way. All right. We have too much products. So the reaction shifts backwards. What should the sign of delta G be at that moment? If it goes backwards, it didn't. So when a reaction goes forward, delta G is what sign? Negative. So if it goes backwards, delta G should be positive. So let's prove it. All right. And we prove it by calculating delta G. So notice this is delta G without the naught because we're not at standard conditions. So let me actually just quick answer this last question. So Q is larger than K. So too much product. Reaction shifts this backwards to form solid, right? And I know that from the reaction of KSP. KSP is always solid, gives you like the different ions and stuff. So you have too much ions, you're going to form solid. All right. So what is the value of delta G given these same conditions? So again, this is at non-standard conditions. So this is where we're going to use the equation delta G equals delta G naught plus RT ln Q. I'm going to use the Gibbs free energy at standard conditions and adjust for the Q that's already, we actually have. Does that sound familiar in terms of cell potential? It's the same thing. It's like the same thing. It's like we have just like these non-standard concentrations or whatever. So let's account for that Q by comparing it or adjusting it from the standard conditions value. So we actually already have delta G naught. R is a constant. We know the temperature, and we just calculated Q. So it's just plug and chug now. So delta G we got up here. Sorry, there should be a naught there because that was coming from K at standard conditions. So this is 1.7 times 10 to the 5 joules. I'm using the joule version because R is in joules. I don't want this to be in kilojoules. So R is 8.314. Temperature is 298. ln Q, so Q we just calculated as 1 times 10 to the negative 22. Whoops. And so if you calculate this part, we get 1.70 times 10 to the 5 joules plus this all is a negative number, so negative 1.25 times 10 to the 5 joules. So we see that when we subtract this number, it's not negative enough. And so we still do, in fact, get a positive value of delta G come out. All right, I'll actually get the value. So we see that delta G is equal to positive 44.5 times 10 to the 3 joules. So 44 kilojoules. So we see that delta G is still positive. So the forward reaction is not spontaneous. But that means that the reverse reaction is spontaneous. I know we were always looking for negative, negative signs of delta G, but it doesn't mean that we can't get any information from a positive sign of delta G. If it's positive, it just means the reverse reaction is spontaneous at those given conditions. And that's what we have here, right? So, yeah, great. So the idea here is that K is related to delta G naught, where if the reaction starts at standard conditions, which way does the reaction have to go to achieve equilibrium? That's what delta G naught means. But if we were given non-standard concentrations, we use the Q reaction or the Q equation with delta G to figure out how does the reaction have to shift from these conditions, not from standard conditions. Right. Okay, so, and it matches what like Le Chalier's principle predicts. Okay, so that's that's chapter 19. So let's move on to chapter 20. Okay, so we have a redox reaction. So I'm giving you a bunch of stuff. So this redox reaction is unbalanced. So I want you to do a lot of things. I want you to get all the oxidation numbers. I want you to figure out what's oxidized, what's reduced. What are the agents? How many electrons? What are the half reactions? And then what's the cell potential? And then finally, what is delta G? So lots of stuff here. All right. So we're going to just go through it fully. I'm going to balance them. I know that the balanced equations are up here, but I don't want us to use it. This is just the cell potentials or the reduction potentials for calculating it later. Let's just work on it from the very beginning. So I like to focus on things that the oxidation numbers are easy to get. So right now I'm looking at this manganese guy. I see that this manganese has an oxidation number of +2. This manganese on the product side has an oxidation number of +4. And I know that because each of those oxygens is a -2. Right? I focus on that because those oxidation numbers are like the easiest to get. And now you've determined that manganese has to be oxidized. So that means chromium has to be reduced, right? Yeah. So yeah, chromium has to be reduced, but we can also prove it too. But that one's just a little bit harder. Chromium, okay, let's get you a different color, blue. Okay, chromium on the product side is +3. That one's pretty straightforward, but it's a little bit more difficult on the reactant side because there's 2 chromiums. So again, if you think charge with oxidation number, you'll be right most of the time, 99% of the time. So I recognize each of those oxygens is -2. So there's -14 coming from the oxygens, but this has to add up to -2. So that means I have to have +12 coming from those 2 chromiums, but there's 2 of them. So it's 2 times 6. So each of those chromiums has a +6 oxidation number. So we're going from +6 to +3. So that, yes, this, in fact, that chromium thing is being reduced. It's losing, or it's gaining 3 electrons. All right. So we did the first one. We got oxidation numbers. Let's do the next thing. So that means, well, let's do B and C together before we balance everything. So manganese 2+ is being oxidized. So therefore, it is the reducing agent. And then that means the dichromate, so Cr2O7 2-. So notice how I'm always pointing to the reactant. We deduce that it is being reduced, so therefore it is the oxidizing agent. All right. So if I ask you what is the oxidizing agent of this reaction, you are looking for the thing that is reduced. If I ask you what is being oxidized, then yeah, you look for what's being oxidized. But if I ask you what is an oxidizing agent, you look for the thing being reduced. So do recognize that little language thing there. Okay, so let's actually balance these reactions now. So you're going to split them up into half reactions. I always start with the oxidation reaction first. So we have a manganese 2+ going to a manganese with 2 oxygens. So you balance each of these half reactions separately. You do the atoms, so manganese is balanced. Next, you do the oxygens by adding water. So there's 2 oxygens, so I'm going to add 2 waters over here. And then you balance the hydrogens with H plus because we're balancing an acidic condition. So there's 4 H pluses on the product side. And then lastly, you balance charge. So manganese is a 2 plus, and then there's 4 plus coming from those 4 protons. So this reaction gives off 2 electrons. So those 2 electrons brings down the product side, so it's +2 on both sides. So the oxidation reaction is now balanced. So then we do the reduction reaction. Let's pick a different, no, it's fine. The reduction reaction, yep, so we'll rewrite the skeleton of the reduction reaction. So Cr2O7 2 minus, arrow, Cr3 plus. So we balance this one on its own as well. So it's atoms, oxygens, hydrogens, electrons. So here I do need to put a 2 in front of that chromium. Don't forget that because there's 2 chromiums there. And then I balance the oxygen. So there's 7 oxygen total. So I need 7 waters. So now I have 14 H pluses. So I'm going to put 14 H pluses on the reactant side. Now you got to be careful with charge. Don't try to take extra care in just inventorying the charge on both sides. So on the reactant side, there's a total of a +12 charge. But on the product side, there's a total +6 charge. Remember, there are 2 chromiums there. There's 2 of them. So that means that this reduction reaction needs how many electrons? 6 electrons, because that 6 brings down that 12, so then it's 6 on both sides. All right. Okay, so those are the balanced half reactions. If you look up here, you should see them. Right there, there's one of them, but notice that, again, this is the reduction. Oh yeah, this is the reduction form, so that's how it is as written. But the first one, the manganese one, it's the opposite. So let's see, where's that one? 4H plus, it's this one. This is the reaction the oxidation reaction we balanced earlier, right? But notice how this one, it's reversed. Because again, what we balanced was an oxidation reaction, but this list are reduction half reactions. Okay, so to actually get the full balanced equation, we need to make sure that our electrons match. So the lowest common multiple is 6 here. So I'm going to multiply that whole top one by 3. So the new coefficients are 6, 3, 3, 12. Yeah, thank you. And then 6. Okay, so now the electrons cancel. Now we just need to be really careful about canceling stuff and adding these up, because water shows up in 2 places and H plus shows up in 2 places. Because I think all of the hydrogens, protons cancel except 2 of them. So this is 2 H plus a plus 3 manganeses plus 1 of those dichromate things. I didn't write water because I see all of the waters canceled except 1 of them on the product side here. So my products are 3 MnO4 or MnO2s plus no H pluses, they all canceled, 2 chromiums, and then 1 water. And that should be the full balanced chemical equation. Check your atoms, check your charge on both sides. So this is +6. Did I do it right? 3, 2, 0. Yeah. Oh, there's 3 of them. Yes. Okay. So there's +6. That's +6, +8, -2, so +6. And then, yep, +6 over there. So all the charge is ready to go, right? Atoms, charge, all of that. And it's all about finding that lowest common multiple here. This is the same thing as N. So N would be 6 for this reaction. All right. So yeah, so N was 6. So let's just keep that on standby because we'll need that a little bit later because we're not done. We got the balanced equation. Now let's get E cell. All right. So this question asks for E cell naught. So we're simply going to do cathode minus anode. We already identified what's the cathode and anode. At the oxidation reaction, that is your anode. And then your reduction reaction, that is your cathode. So we just need to find those reduction potentials for those particular half reactions, which I have up here already highlighted. So here's the reduction potential for the dichromate one. What was that? That's my cathode. So here's my cathode. And then the manganese one, that is my anode. Right? So my answer is going to be, if you take those numbers, cathode minus anode, 1.33 minus 1.23. So I think this is 0.1 volts is the cell potential at standard conditions. If you made 1 molarity of everything, hooked it up, you should measure a fraction of a volt. All right, so that's the cell potential. Notice that this cell potential equation has nothing to do with the number of electrons being transferred. It has nothing to do that I had to multiply the anode by, multiply it by 3. You simply just do cathode minus anode. That's it. Where the N value, the number of electrons comes up is delta G. Gibbs free energy changes. When you do that calculation, that is what N depends on. So the equation that relates delta G to your cell potential is negative NFE. We just got E, Faraday's constant's a constant, and we got N earlier. So just plug in that number we just got. So 0.10 volts, that's your cell potential, times N, which we got was 6 earlier, and then Faraday's constant 96485. Okay, that looks really messy. 96485 coulombs per mole of electrons, and then the voltage we just got 0.1 volts. You plug all those numbers in, and you do get a unit of a joule out. I didn't actually write the answer in the key, but you guys can multiply stuff, right? Times 0.1. So I get negative 57.9 times 10 to the 3 joules. So this is negative 57.9 kilojoules. So what we see is that delta G is in fact negative. This reaction is spontaneous in the forward direction. And that makes sense because we have a positive cell potential that we hook this thing up, and yes, a voltage is produced because stuff happens. The reactants convert to products, generating a little bit of electricity. Okay. All right, so that was a long question for just one question, but it was very comprehensive. We could have, I could have gone one step further and asked you what K is. All right, we can just take that delta G and stick that into our our K expression. The delta G equals negative RT ln K. That's probably like the last thing I could ask you. All right. All right. So let's see if we can't. How much more do we have? Oh, a couple pages. Okay. All right. So here's some conceptual things. Okay. The reduction potential of X plus and Y2 plus to their neutral metals are 0.5 and 0.25, negative 0.25 respectively. What can we deduce about these things? What might help us is if we write the reduction potentials, right? So we're going to start with this first reaction. We start with X plus. This has a reduction potential, I already tell you, of 0.5 volts. So what does the reduction equation look like? If X plus is reduced, its oxidation number is going to go down. So it's going to gain electrons. How many electrons do you think it's going to gain? Just one. Yeah, because it's a +1 charge. So +1 electron makes X solid. So that reaction has a reduction potential of a positive 0.5. So it's fairly spontaneous. That reaction tends to happen. It likes to happen. For the second reaction, this is, I'll do a different color. Y2 plus is probably going to gain how many electrons? two electrons to make Y solid. This has a reduction potential of negative 0.25 volts. Does Y2 plus like to gain 2 electrons? It does not. Okay, so let's see what we can deduce from this. Okay, so which substance is the strongest oxidizing agent? Oxidizing agents are what in a reaction? What happens to them? They get reduced. So we are looking at what substance is most easily reduced. Look for the substance that is most easily reduced. So we are looking for the largest reduction potential. So it's going to be the first reaction, right? Like our eyes gravitate towards this one. This, the 0.5, that's the most positive. But we need to point to the right thing. In this reaction, what's being reduced? Is it X or X plus? What's being reduced? It's X plus. So in this case, it's X plus is the best oxidizing agent because it's the easiest thing to be reduced. Okay. X doesn't get reduced more. So you want to point to the right thing, right? This is important because it kind of changes for the next one. The substance that's the strongest reducing agent. Things that are reduced in a reaction are, things that are reducing agents in a reaction are oxidized. So we are looking for the thing that is most easily oxidized. So that means we are looking for a very high oxidation potential, but I didn't give you those. I gave you reduction potentials. So instead of looking for the highest oxidation potential, you're going to look for the most negative reduction potential, but point to the thing that's oxidized. All right. So here we see X plus really great at being reduced. But X, is that good at being oxidized? No, its oxidation potential is going to be negative 0.5. X is really crappy at being oxidized, okay? Versus, let's think about this, Y2 plus, not very great at being reduced because it's negative. So therefore, if you reverse the reaction, Y solid is actually going to be really good at being oxidized because once you flip this reaction, its oxidation potential becomes positive 0.25 volts. But you need to point to the right thing. In this reaction, what is being oxidized, the forward or the reverse? It's the reverse reaction. So the answer here is Y solid is the best reducing agent. It's the easiest at being oxidized, right? Okay, keep going. All right. So with all that in mind, actually, we probably need these values still. Okay, so the reduction potential of Z plus is 0.2 volts. Complete the statements. So why don't we just write that reduction potential? So Z plus plus an electron gives Z solid. This has a reduction potential of, it says 0.2 volts. All right. So these are all of the equations we are comparing. Let's clean this up a little bit. So we got this one, okay, X plus has that voltage, Y2 plus has this cell potential, reduction cell potential, and then their Z plus has this reduction cell potential. So Z plus is a stronger oxidizing agent than what? Let's remember, oxidizing agents are things that are reduced in a reaction. So we are simply going to just compare reduction potentials. Is Z plus easier to reduce than Y2 plus? Yes, because the number is bigger, so Y2 plus. But is Z plus easier to reduce than X plus? No, so it's just going to be Y2 plus, right? Let's change it. See how it's now Z solid? Now I'm pointing at the products. So now we're looking at the oxidation reactions. Z solid is a strong reducing agent, meaning it's the thing that is oxidized. We're looking at the oxidation potentials. Z solid is a stronger reducing agent than what? Or is it more easily oxidized then what? So something you could do is just simply write what would the oxidation potentials be. It would be negative 0.2 volts. This one would be positive 0.25 volts, and then this would be negative 0.5 volts. So we see that Z solid, this oxidation potential is better than this one. So we see that Z solid is only a better reducing agent than X solid because it's more positive, right? Okay. All right, this one. Oh, this is a completely, okay, yeah, that's a completely different question. So that this is definitely, I don't know, I feel like this part is very, very tricky because it's definitely conceptual, understanding the difference between recognizing how to use the reduction tables and what they mean. You all get really good at doing cathode minus anode, but forgetting that an anode oxidation occurs and you have to flip the reaction, even though in this table, they're all given in the reduction form. One of them has to be flipped in that overall equation or the reaction. Okay, let's keep going. Okay, given these two voltaic cells, determine the standard reduction potential of X. So I give you two cells. Really what we're doing here is using E cell equals cathode minus anode. We just have to be really careful of what is our cathode, what is our anode. So if we look at these equations, lead is being what? Oxidized. So it is the anode. H plus, therefore, is the cathode, but we can check for sure. It's going from +1 to 0. So yes, it is in fact being reduced. So it is our cathode. So, right, when we use the cell potential equation, the overall cell potential, it's cathode minus anode. We get these from the table values. Do we know one of these half reaction cell potentials already? Hydrogen. Hydrogen's is what reduction potential? It is 0. Yes, it is 0. So that means our cathode for this first one is 0 minus your reduction potential for lead. So we can solve for what is the reduction potential of lead in this case. So I think if we get that, so it has to be what? Negative 0.13 volts. That is the reduction potential of lead. Okay, cathode minus anode, both of those values are in the reduction form. I know that lead is the anode, but remember, it's always cathode minus anode. Both of those numbers are in the reduction form. All right, so let's look at the next cell. X is being what? Oxidized, because its oxidation number is going up. Lead is being reduced. So we're going to do the same thing. E cell equals cathode minus anode. We got lead in the previous step. So we see here that lead in this example is no longer the anode. It is actually the cathode. It is being reduced. So it is the cathode. So that means that negative 0.13 is going to go in the cat place. And that's fine. Remember, both of these are in the reduction form. And then minus the anode. So I'm just going to be, solving for what is the reduction potential of this mystery X thing, right? And so I think if you solve for that, you get that the reduction potential of our anode of X is equal to negative 0.87 volts. There's a lot of negative signs floating around, but as long as you always know it's cathode minus anode, they're both in the reduction form, then you'll be fine. As long as you correctly identify cell 1 and 2, or what your species are in each of these different cells. Because notice that lead is your anode in the first reaction, but it's your cathode in the second one. But that's fine. It still uses the same reduction potential. Just place it in the right spot. And yeah, so that's the answer then. Okay. Cool. All right. So keep going. Okay, conceptual stuff. Great. All right, select the correct value for each of the following. Sure. Okay, so maybe what might help you is delta G equals negative NFE. That might help. Delta G equals negative RT ln K. That might help. Okay. All right. So a spontaneous reaction has what sign of delta G? You just yell it out. Negative. Perfect. Okay. A spontaneous redox reaction has what sign of E cell? Positive. Cool. A redox reaction with a positive E cell has what value of K? Very large, yes, because the forward reaction is very spontaneous, that you're going to produce on its own more products. But a reaction with a negative cell potential, so a reaction that's not spontaneous, is going to have a small value of K. And all of this has to do with the signs of delta G too. Positive E cell means negative delta G means large K, right? So all of those things are related by these two equations, really. Okay. What is the K expression for this redox reaction? It's actually an electrochemical cell, but also a redox, it's a redox reaction. But remember, these also have K expressions because we can calculate Q a little bit later. So K, which will be useful for Q later, is equal to the zinc concentration. So products over reactants, the pressure of hydrogen, because notice that hydrogen's a gas here, and that'll be in atmospheres, over, we don't need to include zinc solid because it's a solid, but then H plus concentration squared. So 2 products, 1 reactant. So that's K. So remember, the equation for the Nernst equation, what we actually measure is equal to what the table tells us minus 0.0592 over n log of Q. So what we see is when Q is a large number, when Q is a large number, so when we have concentrations that aren't at standard conditions, when Q is a large number, log of Q is a large number. So what we measure is actually a cell potential that's lower than what we typically expect. So what we measure actually goes down. But if Q is a small number, we actually have a lot of reactants. And what happens is that the measurement we actually make, this cell potential, is actually a big number, because when Q is a small number, then we're subtracting a very small number, or we could in fact be subtracting a negative number if Q is less than 1. All right. So that's the trend here. If Q is big, then what we measure is small. But if Q is small, what we measure is big. That's the idea there. Because this is just conceptually, can you understand how is Q changing here? What is the effect on EMF in the following changes? What if we increase the pressure of hydrogen? How does E cell change? So if pressure of H2 increases, how does Q change? So remember, this is K, but Q is the same thing. It's the same calculation. It's just we're not at standard condition, or we're not at equilibrium. So if pressure of hydrogen goes up, Q also goes up because Q's in the numerator. So if Q goes up, E cell, E cell will decrease because you're adding a lot more product. Q is going to get bigger. You're going to subtract a bigger number. So what you actually predict, or what you see, is a lower cell potential. I always like to think if you pack the reaction with lots of reactants, lots of voltage, good. If you pack the reaction with tons of products, bad, right? The products are like what's spent. So then that lowers your cell potential. So here, what if we add zinc nitrate to the reaction? Zinc nitrate, that's a source of zinc 2+. So zinc 2+ concentration increases. So Q also increases. So here's another example where EMF decreases. Right? EMF decreases because we're adding a product. All right, HCl is added to the cathode. So H+ concentration is going up. How does Q change? It go down. So therefore, your EMF will actually increase in this example. You're packing the reaction with lots of reactant. All right, pH of the cell increases. What does that mean about the H plus concentration? pH goes up. Are you sure it goes up? pH goes up, the reaction or the solution is more basic. Yeah, so the concentration of H plus actually goes down. Because remember, if the pH goes up, hydroxide, or so, yeah, if pH goes up, then if you think about it, remember, H plus concentration is negative log to the pH. So it's a negative to a bigger number. So yeah, it's becoming less acidic. So H plus concentration is actually going down. So therefore Q is actually going to go up. EMF is going to go down. All right. All right, so keep going. All right, the surface area of the anode, zinc solid, is doubled. What do you think? How do you think the EMF changes? Use your chapter 15 intuition. Is zinc solid in the Q or K expression? It is not. So do you think it's going to have an effect? Nope. Yep. So no effect. No effect. All right. Good. Okay. So that's conceptually. I didn't have you calculate a dang thing, but it's how to navigate that Nernst equation. Just simply using concentrations and stuff. Okay. So, oh, we almost done. Okay, so let's actually do some calculations. So here's a voltaic cell, redox reaction. What are the concentrations of everything at standard conditions? 1 molarity. So that means the nickel concentration is 1 molarity. The zinc concentration is 1 molarity. So if we were to calculate the cell potential at standard conditions, we can always go ahead and use the table values. If everything's 1 molarity, you can go ahead and use table values. So we can deduce that zinc is the what? Anode. And then nickel is the cathode. It's going from +2 to 0. So that's the cathode. So cathode minus anode. So what did I say? Nickel is the cathode. So here's my cathode. And then nickel, and then zinc is right here. That is my anode. All right, so cathode minus anode. E cell, because we're at standard conditions, so use the table. Cathode minus anode, so negative 0.28 minus negative 0.76. So you minus a negative, so this is how we get a positive number come out. Okay. Positive 0.48 volts. Okay, that's if we start at standard conditions, 1 molarity of everything. Okay, but once we connect the cell and the redox reaction takes place, how does the concentration of nickel 2+ change? So note where nickel 2+ is, it's right there. As the reaction moves forward, the concentration of nickel 2+ decreases because it's a reactant. While the concentration of zinc 2+, right there, is a product, it increases. So how does Q change during the course of this reaction? Remember, Q is equal to products over reactants, so zinc 2+ concentration over nickel 2+ concentration. When we're at standard conditions, it's 1/1, and Q equals 1. But as soon as we turn on this battery, we just said nickel concentration decreases, so the number in the denominator gets smaller. Zinc concentration increases, so the numerator gets bigger. So as this reaction runs with time, the value of Q increases. So just like before, if Q increases with time, how does your measured EMF, your measured cell potential change with time? It's going to go down. Yes, it's going to go down. So measured EMF is going to decrease with time, just like before, right? This is how you can check a brand new fresh battery. Like, do you have a miscellaneous drawer in your house filled with just random batteries that some are dead and some are not? You know, they have those battery testers that say if it's full or not. Really, all those battery testers are testing for the voltage of those batteries, because they know over time cell potential, it just drops and drops and drops and gets lower. So if you grab a battery, like a fresh Duracell battery, they're 1.5 volts. That's what it says on the package. Like you're paying for 1.5 volts. But if you take a multimeter to a brand new fresh battery, you'll actually read more than 1.5 volts. It'll be closer to like 1.8 probably if it's brand new. But if you leave that battery somewhere, in a device for a very long time and it discharges and you measure it again, it's going to be a much lower voltage at that point. Where if you have it in a device that requires a certain voltage, that battery is going to be like dead because it won't be able to work. So that's how you can tell like a brand new fresh battery to one that's not working as well is if you have a really high peak voltage or if it's diminished over time. And this is why, because as the reaction goes, Q gets bigger, EMF, what you measure, goes down until the battery dies. Okay. Yeah, we did that. Yeah, so EMF goes down. So let's actually calculate it. All right, because we just got when all of the concentrations are 1 molarity, we calculated that Q equals 1. So the E cell that we measure, what we would actually measure is the 0.48 volts. That's what we would measure at standard conditions. But let's say we run this battery for a really long time and we so the concentrations are no longer Q equals 1. Let's say they're this. We have zinc 2 plus is 1.5 molarity and nickel 2 plus is 0.5 molarity. Let's calculate what voltage would we measure here. So the idea here is we calculate Q. I forget, what is Q? It's zinc over nickel, because zinc is a product, nickel is a reactant. So here, what did I just say? I already forgot. Zinc over nickel. Zinc 2 plus over nickel 2 plus. So if we plug in those concentrations, 1.5 over 0.5, we see in these conditions Q equals 3. All right, so we're going to plug that into the Nernst equation. All right, so the Nernst equation, E cell equals E cell naught minus 0.0592 over N log of Q. So we already have the cell potential at standard conditions. That came from the table. So 0.48. When everything started at 1 molarity, that's the voltage we should measure, minus 0.0592. What is N? Let's look at it. So here's the reaction. What do you think N is? Just look at it. How many electrons have to be involved? So just look, how is nickel changing? How is zinc changing? 2, yes. 2, nickel is doing what? It's gaining 2 electrons, and those 2 electrons are coming from zinc. So I tried to make that one straightforward. So yes, N is 2. So this is log of Q, log of 3. And so if you solve for that, you get that the new measured cell potential is 0.47 volts. Wow, so it went down. All right, when we started at Q equals 1, it was 0.48. We made more products, now Q is 3, 0.47. So let's do another one. So we run this battery even more. Now the concentrations are even more different. So let's just do it again for funsies. So Q is still zinc over nickel. So it's 1.75 over 0.25. So that means Q is equal to what? 7. All right, we're going to do the same exact thing, except we're going to plug in Q of 7. So it's literally this exact same thing again. All right, 0.48 minus the log Q, but this time it's 7. All right, so we have 7 times as much product than we do reactant. This has a cell voltage, a measured cell potential of 0.45 volts. Wow, yay, our battery's dying. All right, so let's go even more in the future. We've run this battery for so long that now the nickel is barely there and it's like a butt ton of zinc. All right, so Q is still zinc over nickel. All right, so it's, what is it? 1.99 over 0.01. What is this? If you do that in your calculator, Q is equal to 199. Okay, that's Q. So we're going to do the same exact thing. Start with the cell potential at standard conditions minus all of that other junk. log of Q this time is 199. We have almost 200 more times product than we do reactant. You stick this in your calculator and you get 0.41 volts. So you see that, yeah, even if we change the concentration drastically, it's not going to like plummet to zero. Okay. What you'll see, go if you have a multimeter. Multimeters are kind of expensive, so I don't know. But if you bring one in, if you bring in a battery you think is dead, bring it in. I'll come and measure it for you. You'll see that there is a small amount of voltage that's still produced. It's not, when it's dead, it's not necessarily, doesn't necessarily mean that the voltage is zero. It's just low enough where it no longer works in the device you want it to. It might work in a clock that requires a very small voltage, but it might not work, in the place you intended it to be. So yeah, that's how I test for like good batteries. Like I just go in. See, I'm so lazy that I just throw them all into like a container, and then like the good ones are mixed with bad ones, and then I have to like test them all to see which ones are the best, So yeah, and so we see, yeah, when we have nearly 200 times as much product, the voltage does dip down a little bit there. All right, so that is it. Wow, right at 1:30. So I'll stick around for another like 20 minutes or so if you have individual questions, but best of luck. We don't have class on Wednesday. Yeah. And then we'll finish up chapter 20 and start nuclear chem here soon. Yeah.